Hello everyone, welcome to this first LS-DYNA beginner tutorial. In this video we're going to look at a very simple but very useful crash simulation example, which is a short crash tube impacted by a moving rigid wall. This is a very good first example because it includes many important LS-DYNA concepts. We're talking about material definition, shell elements, contact boundary conditions, and a moving rigid wall, and in addition of course to the output databases. So by the end of this video you should be able to understand the basic structure of an LS-DYNA keyword file, and also to understand what each main part of the model is doing. So as you can see here, this model represents a thin wall tube that's being crushed by a moving rigid wall from the top. The tube is made from shell elements, as you can see, which are like it's commonly used for thin structures like crash boxes or automotive parts, also sheet metal components and energy absorbers in general. So the rigid wall would be moving from from downward towards the tube. Let me adjust it again with an initial velocity, and it will be compressing the tube and causing progressive folding, as you will be see at the end after we finish the simulation. This type of simulation is very common in crashworthiness because we're interested in how much energy the structure can absorb during this impact. All right. And before I start explaining, you have to just remember one thing only, is that we're in LS-DYNA. We usually define the model using we call it a keyword file, right? And this file will contain the geometry, the materials, the contacts, the boundary conditions, the loading, and also the output requests that we want to see. All right. I opened this file, what we call LSP post. This is a free software that we usually use to create our files, especially if you're a beginner. We usually use this free software, but this is just, this is just an interface, right? The original file itself, we can open it with just a simple editor program, very simple, like text, just like you're opening a text file. This is the original file. If you have the ability to write it yourself, you will not be needing, I mean, in an advanced stage, you will not be needing even to use LSP post, and you can write everything and modify anything you like immediately using this simple editor file. Every LS-DYNA, as I said, we call it keyword file. So every keyword file starts with the keyword, which is called keyword, as you can see here. And start, as you can see, any keyword starts with an asterisk, like you see in this one here. And it ends with the keyword called end. Let's scroll down to the end here. All right. So this is for any LS-DYNA file or key file. And between these two lines or these two keywords, we define everything needed for the analysis. All right. So in this file, we have, which is titled short crash tube impacted by a moving wall. This tells us immediately what the model is trying to simulate. And also one note, you see this dollar sign. The dollar sign means that what after it is a comment. It has nothing to do with the solver. It has nothing to do with the simulation. The solver will not be considering it. So this dollar sign, if you want to just to add like some notes to remind yourself in the future, or to tell one of your teams about what's going on here, you just add a dollar sign and you write down whatever you like as a comment or a side note. For example, here we have a side note for units, all right? It tells us what specific unit system we're using, right? We're using here millimeters, kilograms, milliseconds, kilonewtons, gigapascals, and kilonewton millimeters. Um, this is very important in LS-DYNA, because LS-DYNA doesn't automatically know your units, right? You must keep the unit system consistent yourself. Um, this is a very common beginner mistake, that mixing millimeters with meters or kilograms, tons, and that actually can completely destroy your results. I will leave a link for you, for like a table of consistent units that you can rely on, um, um, for LS-DYNA. You can just have a look and you start working. All right, I will leave the link in the description. Next, in this file, we have the control cards. The first important one is the control termination, all right? Um, the control termination defines when the simulation should stop, all right? And in this model, the end time is 20 milliseconds. That means the simulation should stop after 20 milliseconds, right? As you can see, it's just written 20, but I know it's just 20 milliseconds because of the unit system I used, right? That's how important you need to be aware of the units you are using. Um, what we can add other control cards, but let's keep it simple for now. We have the second card, which is the material card. This model use mat cards, material card, piecewise linear plasticity. Um, this is usually known as MAT 24 and LS-DYNA. This is one of the most commonly used material models, usually used for metals. Although I saw it before, actually, to be honest with you, used sometimes for composite material, um, especially if the composite material shows behavior similar to plastic behavior of metals. But usually and most commonly, this material card is used for metals in crash simulations. As you can see, we have the for the material defined or the metal defined, we have the rho, which is the density. We have also the elastic modulus or Young's modulus. We have also Poisson's ratio, the yield stress, and we have the plastic stress strain curve, right? So this is just in the you can see that here in that the editor file or the text file. Well, if you want to see it in a more like friendly way, you can always use software like LS pre-post. So let's go to LS pre-post. Like if you want to see the material card, go to the model and just open keywords and scroll down. I was going to show that at the end, but let's see it now. Mat, as you can see here, Mat 24 linear plasticity. Double click on it. Here is the rho, the density, the Young's modulus, Poisson's ratio, yield, and here we have the, as I said, the plastic stress strain curve. If you want to see the curve itself, you can just click on plot and you can see it here like that. All right, all of that is in the text here written down. All right, here. So this is like the original bit. This is the original source for whatever you're seeing on LS pre-post, right? All right. Then we have here the node keyword. Because as you know, the geometry is defined by nodes and elements. So we have here the nodes. The nodes, as you can see here, for each node, it's defined by the coordinates of each node. We have the x, y, and z. All right. So we have the coordinates of each node. I have to scroll down. It's not moving here. Scroll down. All right, this is the end of the node keyword. Okay. Let's skip that for now, and we must find the shell key. Yeah, here we have the shell element shell keywords, as you can see here. Um, this defines how the nodes are connected to form the shell elements. All right. So as you can see, this file has many nodes and elements lines. Um, you don't need to, like, now as a beginner, you don't need to understand every line, right? You have only to understand that nodes define the points in space. Elements connect these points together so that they create the finite element mesh, right? Of course, in LSP post, we can view this mesh visually, which is like much easier than reading thousands of nodes and element lines manually, right? So the translation for all of these numbers is just the mesh we see here. Let's close that. This is the translation of these nodes and this geometry you see in here, right? Let's go back again. Scroll up to where we stopped. All right. All right. Now we come to one of the most important topics from LS-DYNA actually, which is contact. Let me just highlight it for you. Mhm. Um, well, the thing is, this is commonly used when a structure. This card is called contact automatic single surface, right? And this contact card, this is usually or commonly used when the structure may fold and come into contact with itself. So that's exactly what happened during, of course, when you crush the tube. That will happen, and as the tube collapses, different parts of the tube may touch each other. Um, so this contact card includes friction values as well. We use here 0.8. As you see, this is the friction we use, 0.08 as a friction value. So as a beginner, you should only remember that if the contact is missing or badly defined, the simulation may become unrealistic, right? Because parts may pass through each other. That if the simulation even works, the parts will just pass through each other, and forces may become unstable, or the model may terminate, as I said. So contact is one of the most important reasons that LS-DYNA simulation fails. You don't believe how how many times I created a simulation or a file and kept trying it over and tried to run it over and over and over again and just fails just because of the contact. So it's like became a default for me that when simulation just stopped or it's not running or it failed running, the first thing I always consider is the contact, and it usually is the contact problem. All right. Let's go to the rigid wall. Scroll down. This is the rigid wall card, which is a rigid wall planar moving forces ID. Um, the impact is applied using what we call a moving rigid wall, right? And this is a keyword we can use for that. This defines a rigid plane that moves and crushes the tube, right? So in this file, this simulation we used the wall that has a mass of 800 kilograms, right? And the initial velocity was 8.94 millimeters per millisecond, right? Again, I know that I know these units because the unit system you use has uses millimeters and milliseconds. All right, so this like equivalent to 8.94 meters per second, right? The rigid wall is useful because we don't need to mesh the impactor as a separate deformable body. Instead, LS-DYNA treats this wall as a rigid moving surface. So it's a bit easier and actually faster to simulate. It's very efficient way actually to apply impact loading, especially for beginner examples, right? Now, let's move to the boundary conditions. Um, um, of course, we need to like create some sort of boundary conditions to stop the tube from simply flying away when the wall impacts its surface. So this is done by using the boundary conditions, and the keyword is a boundary BC node, all right, or specific point constraints. And this is used to constrain selected nodes. You select specific nodes on the tube, all right, and we usually um, like stop the tube from moving. And in this model, in this file, we have some nodes are fixed. We made it fixed in all translational and rotational degrees of freedom. These are the nodes we selected, which will represent the supported or fixed end of the tube. Let me explain that on LS pre-post to be easy. Done. Maybe we go for the view. I think the display. SBC boundary. SBC here, right? So we say view all. As you can see here, this point at the end of the tube that we use to fix. So the rigid wall will be coming from up to down, downward, right? So, and here we fixed the end of the tube, so it will not be moving. As you can see here, we fixed all of these nodes, right? So this is what the file is telling us or saying to us, all right? So as a concept, the important note to remember here that the simulation must have a realistic constraints. If the boundary conditions are wrong, the results will not represent the problem you're trying, the physical problem you're trying to simulate, right? So finally, we have to define the output databases. Let me scroll back up. I should have made that more arranged. Sorry for that. We have here the first one. This is database GLSTAT. This like to allow us to see the global energy information. Then we have the database MATSUM, this one here. This is usually used for material energy summaries. Then we have um, the database for rigid wall force. This is to see the rigid wall force. Um, and we have the database node output. This is for like the nodal output, like displacements, velocity, acceleration, etc. And for the animation results, we have the database binary D3 plot. The D3 plot file is what we normally open in LSP post to see the final or to see the simulation or the deformation and the stresses and the stress maps and the strain maps and the animation itself. All right, and the for the rigid wall force, I won't say it's this output is especially important in this model because it gives us the rigid wall force, and from this we can actually plot force versus time or force versus displacement, and of course for crash worthiness, these curves are often more important than just the animation. And the animation just tells us what happened visually. Um, and the curves would tell us whether the structure is performed well or not. So these are the main structure of the file itself. Okay, as I said, You can use, I will go back and in a bit now to the LSP post file. Let me just close this one. All right. You can just modify the file directly, or you can do everything you want in LSP post. And just to go through LSP post, here we have this is the material card we started with. All right, you can just this is the specific material card we have, MAT24. And if you want to see the rest of the material card, you just can go to all, press here, and you can have here all of these are different. This is the one we're using, it's highlighted in blue. All of the material cards you use for different all sorts of engineering materials, all of that, all the way. We also discussed the rigid wall. This is the material card for rigid planar moving forces. If we open it like that, we'll see, as I said, we have 800 kilograms as a mass and the initial velocity in this card in here. We saw the boundary condition, the SPC nodes, and this is the material card for contact. We're using automatic single surface. You can just, add whatever you like in here and just save the file, all right? If, let's say, you want to modify something in a kind, in a fast, even if as a beginner, you can just, you want to modify something in the file itself in a kind of fast way. So instead, let's say I want to modify this 200 modulus, Young's modulus from 200, let's say, to 400, all right? So instead of opening the software itself and doing all of that, you can just open the file, scroll down to the material card, and reach the value here and just modify it to make it like 4. It will now 400 gigapascal. But you have to be very, very careful, because each parameter uses like 10 spaces, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is for the material ID. All of that, this segment here, is reserved for the material ID. For the density, also had 10 spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of these 10 spaces are reserved for the density. Anything written after that space, starting from here, will be counted for the Young's modulus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All of these spaces are reserved for the modulus. And the same applies for all parameters, for everything, except some special exceptions. I'm not gonna, talk about it now. It's related to the coordinations, but it's not important for you as a beginner right now, right? So if you want to adjust a parameter, you have to be very careful. Like if I did something like that, let's say you want to like add a number here. Let's say I want to add 8. See, there is a shift happen. See, when I write like a number, the shift happen. No, we don't want this shift to happen. So we're gonna highlight the space I want and write 8 so that no shift would happen whenever I add or modify a number, right? If even you want to delete it, just replace it, highlight it, and replace it with a space, okay? Because this is very sensitive, and anything you do in that file will be reflected in the how the solver would read this file, right? So now I will start running this file and see the final results and how it would would look like in the simulation or the animation.